Time feels the same for most of us. We wake up in the morning. We go to sleep at night. 1 hour is always 1 hour, a steady and predictable march forward. But this feeling of constant universal time is an illusion. It's a product of our very specific circumstances here on Earth. In the vast emptiness of space, time can behave in ways that defy our everyday intuition, especially near objects of immense mass. It can slow down. It can stretch. This is not the stuff of magic or make-believe. This is the reality of physics. Our journey into space is also a journey into the very nature of time itself. The idea that time is not absolute is a cornerstone of modern physics. For centuries, time was seen as a universal clock, ticking the same for everyone. But Albert Einstein's theories of relativity shattered that notion. He showed time is not separate from space. They are woven into a single, four-dimensional fabric called spacetime. This fabric is not flat or rigid. It is flexible and can be warped and bent by mass and energy. That warping is what we experience as gravity, and it changes the flow of time. Imagine time as a river flowing through the universe. On a flat plane, the river flows steadily and evenly. When it encounters a deep valley, its course changes. The water might speed up, slow down, or pool. Likewise, the river of time is affected by the landscape of space-time. Where gravity is weak, time flows at its normal rate. Near a planet, a star, a black hole, the river of time slows to a crawl. This is gravitational time dilation. If a planet like Earth creates a small dimple in space-time and a star like our Sun creates a larger depression, then a black hole creates a bottomless pit. A black hole is what remains when a truly massive star collapses under its own gravity, squeezing an incredible amount of mass into an infinitesimally small point. The resulting gravitational pull is so immense that it warps space-time to an absolute extreme. Cross the event horizon and nothing, not even light, can escape. It is near this event horizon that gravitational time dilation becomes truly mind-bending. The closer you get to a black hole, the more severely space-time is curved, and therefore, the more slowly time passes for you relative to someone far away. Imagine you have a brave astronaut friend who travels near the event horizon while you watch safely from a distant spaceship. As your friend approaches the black hole, you would see their clock begin to tick slower and slower. Their movements would appear to be in slow motion, taking longer and longer to complete. From your friend's perspective, however, everything would feel completely normal. Heartbeat, thoughts, watch, all ticking 1 second at a time. Time is always normal for the person experiencing it. The difference becomes apparent when you compare two frames of reference, your friend near the black hole and you in deep space. If your friend were to spend just a single hour hovering near the edge of the black hole and then return to you, the consequences would be staggering. While only an hour passed for them, decades, centuries, millennia could have passed for you and the rest of the universe. They would return to a future they never knew, having aged only slightly, while everyone and everything had raced ahead. This is the ultimate expression of time dilation, a naturally occurring, one-way time machine into the future. The film masterfully uses this exact principle as a central element of its plot. Astronauts journey to planets orbiting a supermassive black hole named Gargantua to find a new habitable world. Their biggest enemy is time itself. The first stop, Miller's planet, sits so close that gravity creates a dramatic time differential. On Miller's planet, 1 hour is equivalent to 7 years for those outside its deep gravitational well. To achieve that extreme, the planet must orbit near light speed around a rapidly spinning black hole that drags space-time along. Their brief visit goes wrong and costs 23 years. A crewmate ages alone. The human cost is devastating. Gargantua's look, a warped, glowing accretion disk with light bent around, is grounded in real relativity mathematics. But the wormhole is speculative. Possible in equations, yet unstable without exotic negative energy matter. The giant, perfectly timed waves are dramatic. Extreme tides are likely, but such regular mega tsunamis are debatable. The ending, Cooper entering the black hole and finding a five-dimensional tesseract to message the past, is storytelling, not established physics. No one knows what happens inside an event horizon. Our laws break down at the singularity. Think of it as science-inspired fiction that keeps the heart of the idea honest. Time dilation isn't just sci-fi. It's how the universe works. We even correct for gravitational and velocity-based time dilation to make GPS accurate. Satellites run about 38 microseconds per day, faster than Earth clocks. Engineers correct it, or maps drift by kilometers. Future high-speed or deep gravity missions will feel time differently from Earth, raising logistical and human questions. Interstellar uses real physics to explore love, loss, and our place in the cosmos. It inspires us to keep exploring the strange, beautiful dance of space and time.